Hello, so this is my representation of Lab1. Here we've already created an experiment called EE542 Lab1. We've already swapped in to avoid the time that we're going to take to swap in because it's going to take a long time for us to find the nodes and swap in. So I've already swapped into the nodes. As you can see here, these are the nodes and these are the node IDs. Now the main idea is we use a NS file. In this case, we're using this NS file, and it also shows us the visual representation of our NS file, which is something like this. You can see here that node A is connected to node B, which is connected to node C, and in turn is connected to node D. In the NS file, we specify that we have 4 nodes such that link 0 connects A and B, link 1 connects B and C, and link 2 connects C and D. We've set a specific OS on node A, say the cent OS. Here we are trying to set the we are trying to install RPMS automatically. In this case, we're using wget, this one. And we are also trying to install cmatrix.tar.gz automatically, so this tar file as well. Along with that, we're trying to run this program, which is sample.sh automatically as soon as we execute this experiment and the NS file is uploaded and we swap into the nodes. So to show this, let's pick out a node. In this case, so let's clear out this screen, and so we can SSH into any of the nodes based on the node IDs. For example, if you want to SSH into node A, you just have to put in the node ID, which is HPC36, and it asks you authentication, and you say yes, and we enter node A. Similarly, we can SSH into node B using its node ID, which is PC46, and we see that we are into node B. So last one, which is to see that we've automatically installed our specific program that's run automatically as soon as we swap in. So I've created a sample shell script. Looks something like this. So here we have sample.sh. I'm going to open it. So the point of this sample.sh is just to print out hello Saurabh, which is my name. Set this, and the point of the code is to generate this log file such that it prints it when it was executed, which it has created, as you can see here, test1.log. So when you open test1.log, you will be able to see what exactly was printed by the shell script that was executed, which in this case was hello Saurabh, which is what we wanted to print. Now, moving on, for us to prove that this RPM was correctly installed, we can check it in the details part, where it's going to show us that this RPMS was run automatically when it was swapped in, and similarly the tar file as well was installed automatically in a similar manner. So this is my representation of showing you that we can install the RPMS and the tar file automatically, as well as run our own .sh file. What I've also shown is so I also ran this other barrier code. So as you can see here, I wrote this special code called start.sh. And so the configuration is pretty much similar. Instead of having the different links, we have something like this. And our idea was to run start.sh such that nodes A, C, and D were going to be the slave nodes, and node B was going to be the master node. So start.sh contained a special code which is something like this. So start.sh is stored in this location. going to open star.sh. So this is one of the codes that I've written for barrier synchronization, such that we have all the nodes starting at the same time. So for that purpose, I wrote that if it's the master loop, which is in our case that's a loop, that's the node B. We have it enter this one, and then it prints out in master loop and it reaches the barrier. And similarly, if it was a slave node, which is nodes A, C, or D, we are going to have it print in else loop applying booted along with the name of the node, and then we print it done. So to confirm that this worked perfectly, we also we printed the output of the sh file into 4 log files, such that node A would write into SE558AY1.log, node B would write into SE558AY2, node C would write into SE558AY3, and node D similar to AY4. So if we open up say SE558Y log, we will be able to see this output, which is binary synchronization in else loop. It prints out in else loop because node A was a slave node, but you would see a different output in the log file which was modified by node B. So node B modified AY2. Then open that, and as we see here, it shows that it's in master loop, reached the barrier, and it prints out done. So we can see here that it was executed correctly. The master node, which was node B, wrote in a different file, which is SE558AY2, with different contents compared to node A, and we can also check node C, which should have the same contents as node A, because it was also a slave node, except it says that it was node C. As you can see here, in else loop, apply and quoted node C is printed out here to confirm that. So we exit this, and this is my representation of Lab1 for showing barrier synchronization. Now I also have one more experiment to show that we were able to form static routing as well. As you see here, we have 4 nodes, and we have a similar kind of setting where node A is connected to node B, which is in turn connected to node C, and which is connected to node D. So node A is only connected to node B, so it does not have a direct route if you try to ping to node C as well as node D. So we had to write a special line in the NS file to specify that if node A wanted to contact node C or node D, its job was to send it to node B, and node B would decide who it should send to, either to node C or node D. So this is a NS file that we used. We have 3 links, as you can see here. Link 0 is between node A and node B, link 1 is between node B and node C, and link 2 is between node C and node D. We set up to Ubuntu 16.04 and 2 nodes A and B. We could do it for any number of nodes that we've created over here. We could do it for node C and node D, choose whatever OS we needed. And here we set up manual routing. So as you can see here, we add a route for so for A to reach C, it needs to go to D. Similarly, for we say that if D wants to contact A, then it has to send it to B. Similarly, we have to say that so if node C was to contact node A, then it has to send to node B. If node A was to contact node B, then it has to send its packet to node B. Similarly, if node B wants to contact node D, it has to send it to node C. And we added a special kind of route here, so that since node A cannot directly decide who if it wants to send to node D, so we say that if node A wants to send it to node C, it has to send it via node C, but it has to first send it to node B. And yeah, so this is what the NS file was written as. So to prove that our manual routing worked, I've SSH into each of the nodes, which is node A, node B, node C, and node B. So let us first take node A and show you what happens. So as you can see here in the visualization as well, we have a 50 millisecond delay between each of the links. So if we ping, we should expect a round trip of 100 milliseconds between any two nodes that are directly connected. If it has to go through another node, then obviously we expect an extra delay. So I'm going to show that when we ping. So when we try to ping node B, we are supposed to see a delay of 100 milliseconds, and that's correct because 50 milliseconds across the link and then it's to and fro. So we have 100 milliseconds. Now if we try to contact node C, to contact from node A to node C, it has to go through node B, so we are passing through two links, so we are going to expect twice the time for it to return, so 200 milliseconds. That's exactly what we see here. Similarly, if we try to contact node D, now node D is connected by a 3 link, so we should expect a delay of 300 milliseconds, and that's exactly what we see here. So node A is obviously able to contact all 3 nodes. Similarly, we can check out if node B is able to ping all the rest of the nodes. So node A is directly. So this is my representation. Now I can also show you that when we modify the experiment, you can change the NS file over here. So you can either choose a different NS file, or you can edit the specific NS file to change it, and then we have to modify it so that the NS file is modified. Now what we can also do is we can modify the traffic shaping, that is change the delay. So let's do one thing, let's change the delay on all the things to 20. This is 20, and change it, and let's say this is also 20, and change this to 20 as well. So here we change the delay across each link to 20 milliseconds instead of 100. So let's go ahead and execute it. Gone ahead and executed it. We should see that there's a difference in the delay when we try ping the nodes now. See if that took effect. Ping node B. You see here the delay is now 40 milliseconds because we changed it to 20, so it's 2 and 4, so it's 40. We were to ping node C from node A, then we see 80. It's again cross out. We see a little bit of difference of millisecond because of the actual delay in the data nodes. Cannot expect it to be accurate, especially when you're considering very small delay. We go ahead and do node B now, and it should be 120. That's exactly what we see here. So this did take place. So we can change just not this, we can change the bandwidth, and we can change the loss ratio as well. So if we increase the loss, what happens is as you see over here, there's a 0 packet loss because we've not introduced any loss. If we increase the loss, we can see a lot more packet loss. If we put in a loss ratio of 1, that means no packet can go through. There's 100% loss. So one of the packets will be received, and we see 100% packet loss when we try to pick. So this was my representation for Lab 1. I believe I've covered all the important topics. Hope you enjoyed my tutorial. Have a nice day. Thank you.